in this revision series of module 2 of COA, now we have to we were having this program, and with this sample program we have learned the single cycle processor. So the first was this address scheme, and in this address this was the instruction which has came, right? So this is a load instruction, that is an I-type instruction. So in I-type we have an immediate value, 12-bit immediate value was there in the I-type. Then there was RS1 value, function 3, and also the next thing that was there, the RD value, opcode. Okay, now this is a I-type. So I-type's opcode is this. So we write that opcode here. Fine. Then we have the RD, RS1, the immediate value. The immediate value here is 4. Now this 4 minus 4 it is. So you have to write the 1's complement of it, add 1 to it. Then you get the 2's complement. Then you will get this 12 bit, you have to represent that. Then RS1 value is what? This 6. So the RS1 is X9, right? That is the RS1 value. And RD value is this S6. So that also you have to add it here, 5 bit. Okay, in this way you got this instruction. Group it in 4, group as 4 groups. You're going to 4 in each group, 4 bits. In that way you're going to group and you get the machine language from it, right? So this, how we did it detailing was there already, we have discussed. Okay, so I hope you don't want to go in detail in that. So this is I-type instruction. So in this I-type instruction we are loading a value from the memory. What I'm going to do is that we're going to access this data from the memory, and I'm going to write that into this S6 register. That is what is happening here. So what this instruction means, in the memory is this position, from the memory is this position. I'm going to access this address from the memory, and I'm going to read the data which is present in this address position in the memory, and that data which I have read, I'm going to write it into this register S6. So how we are going to write? First of all, our this instruction is coming. Okay, now in this instruction here this is 12-bit, 5-bit, 3-bit. Okay, now why we know loads function 3 value is 0, 1, 0. That is why we have put this function 3 value 0, 1, 0 here. Fine. Now in this instruction what happens, the PC would take this address, that is 0x100, that is the address of this instruction, and give it to the instruction memory. Now I have to take the instruction which is present at that address, that is at address 0x100. What is the instruction which is present is this machine language code. That instruction we will get. Okay, in that instruction this RS1 value I have to give to here, because from that RS1 I have to read that value. RS1 contains X name. That value I have to read, and that value I have to subtract with 4 to get the address. That I have to give to the data memory, right? So here what happens is that in that instructions 19:15 is what? 19:15 is the bit address. That is 19:15 is this RS1 actually. Here if you see, right here if you see, I will just a little bit zoom it for you. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So this we started with 15, 19. So this 19:15, this bit cut is in RS1. So first I have to take that, read the value which is there in the RS1 register. So I am giving that RS1 value, that is this address, that is this 9 I am giving to this A1. Whatever value is there in that 9 is 0x2004. That I am going to read it out. That I have to add with -4. With this immediate value I have to add this address. So now what happened is that, wait a minute, okay. Now what happened is that there is extender. Now our immediate value is so immediate value is what? 4. That immediate value, that is 0FFC, is 12-bit, right? It is 12-bit. If I group it, 1 group, 2 group, 3 groups only I get. So that is why it is 12-bit. I have to extend that into what? Using the extender. Since it is negative value, we will add 1, 1, 1 at the last. So that is why when I am extending, I am getting FFF. I am going to extend that immediate value to 32-bit. So that is why we are using this extender. Now that value along with this read value that we got, you are going to add it. Now ALU controller 000 means what? You are adding it. Resulting, you will get an address. Okay, that address you are going to give into the data memory. Okay, and you're going to read the value which is there in that address. So here from this address I got 10. Let us say in this address there is 10. That value I have read it out. Okay, then I have to give it to WD3. Okay, WD3. Now I have to write it into S6 register. So from here, this is my S6 registers that I would give. This S6 I would give through the A3, and value which I read, that is 10, I have passed it to the WD3, and reg write would be 1 because I'm writing into the register. So my reg write would be 1. And that data what we have write would come into the register. This is how we are done the load instruction, right? This is how we do the load instruction here. So whatever value we got from the read, that we pass through the WD3, right? And the register to which we are writing, this is S6, that will pass through the A3. Fine. Fine. So this is done. Now I have to execute the next instruction. For that, the PC's this value I'm going to add with the current instructions value. I'm going to add it with 4 to get the next instruction value. Understood? Fine. This much we have understood. This is how we did the load instruction, and this is what we have already discussed in the previous videos, this I type, S type, and all. So here what happens, the description of what happened is given here. Now why we use the immediate extender, like to extend it to 32-bit, all these things are given here. Since it is negative value, we are adding 1 to the last while we are extending. So these part you can just read it out from the notes, so you can easily find it, get it. But still right now I have completely explained the load instruction cycle, so I hope you understood that. And if you have still doubts, it's because you haven't learned the module 2. This is the revision series, right? So the detailed explanation to the module 2 is there in our channel, so that if you go to this channel, click the playlist, right, you can see the CO module 2 complete 19 videos are there, so you can just watch it from there. Okay, fine. Now let's come back to what we are doing right now. Next in our is our store. So here if you see, the next instruction that we are going to execute is, if you're looking at this, so now the PC plus next instruction at this address is a store instruction, which is S type instruction. So in the S type instruction, we know we have an immediate value, we have RS2, RS1, function 3. Immediate is actually split. First 7-bit is coming here, next 5-bit is basically coming here. Then we have the opcode. For S type, the opcode is 01000011. Okay, so here if you see how the immediate bit has been calculated, here my 8 is my immediate bit. So what I'm doing is that I'm going to write 8 in what? 12 bits first of all. I have to write 8 in 12 bits. So here if you see, guys, here if you see, 8 when you are finding in 12 bit, it is 0 0 see 0 1 2 3 2 raised to 3, right? That is 8. Then rest 12 bit it is, right? Now what happens, guys? 1 2 3 4 5 6 7 8 9 10 11 12. This is how I write 8 in 12 bits. Now here if you take here the 7 bits, you have to put it here, and the rest 5 bits you are going to put it here. So 7 bit would be what? 1 2 3 4 5 6 7. These are my 7 bit. That 7 bit I put it here. The rest 5 bit is 0 1 0 0 0. That value I have put it here. Now since it is store SW, then the function 3 value is 0 1 0. That we have right. Then we have right RS2 is 6. So that in here. RS1 is this 9, that we have write it here. Then opcode for the S type. Then group it in 4 and you get the machine language. Fine. How you going to group it? That is also table is given here, guys. Every table is given here. Okay, where is the table? I will show you how we are going to group it. Here you go. This, see, 0 means, like, if you group it first, 0 4 0 0 means it is 0, 0 0 1 means it is 1. So you can just check out this table. Everything is in this note itself. It's like a 100 on 100 note it is. Okay, fine. So now we have this. Now we are doing the store instruction, right? So when you're doing the store instruction, I'm going to see this is how the store is basically done. So we know, while I'm doing the store instruction, first what happened is that rs to rs1, I have to read this 2 registers value, and the that is my rs1 value, I have to add 8 in the rs1 value. And in the S6 address, what I have to do is that in this S6 address, I have to write there. That is, if in this S6 there would be some value, right? So that value you have to take, and that value I have to write in this address. So guys, okay. So here if you see, this 8x9 is an address. Whatever be the address, in S6 there would be one value in that register, that you want to take the value in that S6 register, and what value you got, that value you're going to write into this address 8x9, you're going to write that value here. Fine. So here if you see S6 is here, x9 is there. In the x9 you got a value that you're going to add it with what? You're going to add it with the immediate value. Fine, you're going to add it with the immediate value, like how you did. If it was 0x008, that you extend it. Since it is positive value, you're going to extend it by adding zeros only. That you add, you got an address. Okay, in that address I have to write this x8 value. That means that is in S6. I read the S6 and I got that in S6 there is 10. That I have to write in this address. So this address I am calculated using the RD1 value, that is 9th register. There were one address that we put in the ALU. The immediate extender would give us 8. We add that both. ALU control, you can see it is 0 0 0. That means we add that both, and that result you're going to give to our data memory. A you're going to give, and at that address you want to write. So here memwrite is 1. There is no reg write. That is why reg write is 0. If you see, immediate SRC value is 1. Why immediate SRC value is 1 here? Because here our immediate is split. So if my immediate are split, I have to combine both of this immediate from this part and this part. So in order to combine that, my immediate SRC value is 1. Now my memwrite is 1 because at this address I have to write the value which I got from this S6 register, which is 10. So I am putting it here in the WD, and memwrite becomes 1. Fine, that is how this process ends here. So here you have to note that there are 2 important signals that you have to find here. First is the memwrite become 1. Now the next thing is that whatever you have done here, immediate SRC. Why the immediate SRC value is 1? See, here immediate SRC is there. That is 1 because S type is splitting the immediate. So we have to combine that immediate splitted immediate values. So to combine that splitted immediate value, you are having this one. So now ALU SRC. Now there is similarly ALU control is what operation you are doing here. There is one thing called as ALU SRC. Now for load and for store, the ALU SRC is 1. For all other, it is 0. While you are doing some things in the memory, right? Why load and store you are having the ALU SRC to be 1? Because we are taking the value from the immediate to add here. Source SRB is the. From here immediate you are taking the second operand to add here. That happens only in load and store case. Understood? In other cases we are not doing that. So ALU SRC is 1 in the case of load and store. For add, sub, and, or, and, or, directly the instruction is basically adding here, so it is 0, 0, 0 itself. But load and store, ALU SRC is 1 because in the source B, immediate extender is coming in the source B. That is something also we have discussed previously itself. So when is immediate SRC 1? Immediate SRC is 1 because in S type, if you see, the instruction is split into two. Upper 7 bit is here, lower 5 bit is here. So what happened is that we have to reassemble these extent unit needs to be reassembled these into two pieces, which require a different selection logic than the symbol, because we have to split, it is split, so we have to combine them. So that is why we are having the immediate SRC. But when we consider the I-type instruction, the immediate SRC is 0 because immediate is not split in I-type instruction. But in S-type, the immediate is split. That is why in S-type, we have the immediate value to be 1. In S-type, the immediate is split. But in I-type, the immediate is not split. So that you have to understand. Now, all other instructions seen so far uses immediate SRC, and R-type doesn't even uses the immediate value, so we don't care what is the immediate. Now if it doesn't use, if nothing uses immediate SRC, that means if in R-type and all, it is between the registers only, there is no immediate value. So if the R-type and all doesn't use the immediate value, then immediate SRC would be X, that is null. Don't care, not null, I would say, it's don't care. We don't care whether it be 0 or whether it be 1. It doesn't affect there because R-type doesn't uses that, right? So in here you have to understand the ALU SRC and immediate SRC. ALU SRC is 1 when you're using the source B's value is from the immediate. From the immediate the source B value is coming, then ALU SRC is 1. Otherwise, if it is from the registers the source B value is coming, then ALU SRC is 0. Immediate SRC is when the immediates are split, then immediate SRC value would be 1. Otherwise, it would be 0. Cool. Now, let's understand about ALU now. In ALU, if we see here, there is one important thing that you have to understand. This is our ALU instruction, let us say. We have our RS1 value and RS2 value here, and then we have the RD value, which is the 4. Here if you see, how is the order? Function 7, RS2, RS1, function 3, RD, and opcode. Opcode for R-type is 0110011. Okay. So we have write them in the machine language form. Like this, you will get a machine language by grouping them into 4 bits. Fine. Now, here what happened is that we are taking the value from S5 and S6 and we are adding them. Okay, so from S5 and S6 we are taking the value and we are adding them, so we are not taking anything from the immediate. So the source B is coming from what? The source B is coming from RD2, that is the S6 and S5. Both these values you are going to give it to the ALU. So there would be a multiplexer used. Now why this multiplexer used? As I already said, this multiplexer is used to decide whether we are taking the source value from the immediate or from this register. So since I told you that ALU SRC is 1 when you are taking it from the immediate, so here ALU SRC should be 0 because we are taking it from here. Now it is OR operation. Sorry guys, this is OR operation. So now we need to do the OR of it. Okay, since I am doing the OR of it, whatever I am doing the OR of it, and that value that I got by doing the OR, I have to put in this X4. That I have to directly, I have to give it to what? The register WD3 to write in there in the S4 register. That, so I don't want to pass through the memory. It doesn't want to go through the memory. It can skip the memory part. There is a multiplexer to decide whether we are taking the data from the read data or whether we are taking from ALU SRC. Now when result SRC is 0 means I'm taking the data from ALU. If result SRC is 1 means I'm taking the data from the memory. Here I want to take it from the ALU. So my result SRC is 0. And immediate, as I told you, it's don't care. Now when result SRC is 0 means what? I'm taking from the ALU and I'm putting that value into the register, and reg write is 1. Fine. Now it's OR. So for OR, it is 0, 1, 1 is the ALU control. So you may think, how can we decide about the ALU control? So if you see here, there is one table that I would like to show to you. There was one table which was there, I think. So ALU's table is not seeing right now. Okay, say ALU control, that is for OR. It is 0, 1, 1. Okay, so that means we are ORing this. Okay, the result that we are going to give, we have to directly give it to the register. So there's a multiplexer that is deciding whether from the memory we have to take the data or whether from the ALU we have to take the data. Now if I have to take the data from ALU, then there is result SRC. So here if you see, there is a result multiplexer. Okay, sometimes the load, if it is in the load instruction, we take it from the data memory, but here R type we have to take the data result from the ALU. So multiplexer would decide. Result SRC is 0 means what? Result SRC is 0 means we are taking it from the ALU directly. That is what we are talking about. We are taking it from the ALU directly here. Now you may ask why we don't care about result SRC in store. Because store, we are not going again to the register back. If you are going again to the register back only, you care there. But here we are not going to register back in the store, right? So that is why we don't care about the result SRC in there. Here we have reg-write. So in R type, reg-write is 1. Okay, but there is no mem-write. And result SRC is 0 and ALU SRC. Now ALU SRC from the source B we are taking. Source B is from the immediate, then it would be 1. But here source B is from where? The source B is from the register. So this value would be 0. But ALU SRC for load and store would be 1 because source B value is from the immediate. Now result SRC is don't care for store. We don't care because we don't deal with the result SRC in store. But result SRC for R type was 0 and for load it was 1 because we are taking the value to write into the memory from the data memory. Fine. Now mem-write. Mem-write is there in store. Others there is no mem-write. Reg-write is there in the R type as well as in the load type, but it is not there in the store. Now this is all you have to understand about R type instructions. Also we have understood clearly. Now we have branch. In branch, what does branch means? What does branch equal to do we know? If RS1 and RS2 are equal, then we have to jump to this part where we have to jump to PC plus this offset value. We have to go. So here what we are going to do is that how does this comparison happens? If RS1 is equal, if RS1 minus RS2, if it is done using the ALU, what happens is that if you subtract RS1 and RS2, if the result is 0 means they are equal. So we have to take the branch. If the result is not equal means we don't need to take the branch. It will do the normal execution, that is PC plus for normal execution it will do. So that means PC plus sign extent offset would give us the branch target. If it is new, PC plus offset we have to do to get where we have to jump. Otherwise PC plus 4, the normal execution. If the branch becomes equal, then we have to go to PC plus offset. Otherwise we have to go to what? PC plus 4, the normal execution. So now here what happens is that for subtraction ALU control is 0, 0, 1. That you have to understand. Now here if you see, this part you have to understand here first of all. Now what happens is that when ALU subtraction, what it will do, check RS1 is equal to RS2. So if you got a 0 from that result, that by subtracting RS1 and RS2, that means you got a 0 flag from ALU. When you got a 0 flag from ALU, what happens is that it will compute PC plus the immediate extent. Now PC mux, there is a PC mux which would decide whether I have to use PC normal execution PC plus 4 or whether I have to go to PC plus immediate, whether I have to go to the branch. Now PC SRC is a control signal that select which PC value you have to choose. Whether I have to choose the PC mux is the PC SRC is a control signal in that mux. Fine. So here if you see, there is another important thing. PCSRC's branch and 0 is how the PCSRC is calculated. Now I will tell you one important thing here. How can you find the offset? Offset is target. Which address you want to go minus the current PC address would give us our target value. Okay. So the immediate value here becomes minus 12 here because the current instruction branch is equal to this. And it says that I want to go to L7. So if I want to go to L7, then my offset is what? Where I want to go, the target, because we know where we want to go, that is the target is equal to what? Target is equal to the current PC instruction plus offset. So if my target is given to me and if my current PC is also known, how can I find the offset? By subtracting the target minus the current PC value. So here in the instruction of the branch which is asked in the question, our target is L7 and L7 has this address, target address is this. So we subtracted, we get minus 12. So my immediate value becomes minus 12. Now we know here this is how the B type, in B type the immediate is actually splitted. So it is splitted into 4 locations, the immediate value is splitted here. And it is a 13-bit and it is splitted into 4 locations. So that means if you have minus 12, that means here 0 0 is when in the load, when you nothing is split. 0 1 we got for store, when only 2 places it is split and we are combining them. But when 4 places it is splitted, in 4 locations it is splitted, then it is 1 0. My immediate SRC is 1 0 when it is splitting into 4 bit. So that means how 1 bit is from 31. So in INSTAR 31 we will write 1 bit, and then another bit would be in the 7th position, and 30 is to 25 there would be another bit, 11 is to 8 there would be another bit. So now how can you write that? How can you? A minute guys. Here you got let's say minus 12 value. Okay, if I'm taking this my first slide where it is there, here if you see, 1 minute guys, here if you see, this is my current address position. Okay, this is my current PC value and I am jumping to L7. So this is the address which I have to go. So that means I will check whether S4 this are equal. So my immediate value I got minus 12. So how we are going to split this minus 12 is that the immediate value has to be splitted how? Here, that you have to understand. 131, then I told you 31 is to 25 you have to do.